Good afternoon, this is Schweitzer, and we're looking to get close to wrapping up our modeling of atoms here as far as ground state versus excited state. Now, what does it mean, ground state? Well, ground state simply means it's in its lowest energy state. So, we know we have these electrons in atoms, and we know there's orbitals and there's suborbitals, and everything we've done so far has just been in the ground state. So for example, if I were to do, let's say, carbon, okay, well let's do oxygen. Oxygen would be 1s2, 2s2, 2p4. That's electron configuration. So, or if we did a Bohr diagram, it'd be 1, 2, 3, 4, 5, 6. And I'm drawing in a certain way to kind of mimic this. These are my two, actually 6, 1, 2, 3, 4, 5, 6, 7, 8. There we go. So these two are this two, these two are these two, and these two are these two. So, but the basic theory here is that comes along energy. Now this could be a photon. Well, they aren't really saying it here. I wrote the wrong spot here. But energy comes and takes an electron and excites it to a higher energy level. This is just basically energy. Now looks like they're adding a photon to it. Okay, which is fine. It could be another electron or energy of some sort. Comes and hits it and absorbs energy and raises it to a higher level. We call this spot here the excited state. So I could draw this out as a Bohr diagram and in another way. I could do, okay, plus, and I could do something like this where I have one and then maybe even take two of them, doesn't matter, and then 1, 2, 3, 4, 5, 6, 7, 8. Is there anything wrong with this? Just one of my electrons got bumped to a higher state. This is just an excited form. Not really anything wrong with it, but we do want to realize that when it comes back down to its excited state, which really happens pretty quickly, it's going to give back that energy, and that energy is usually in the form of a photon. Well, not usually, it is photon. And the energy of that particular photon is reflective in the energy differences between these two energy levels. So that tells us a little bit about that atom. And of course, we couldn't get any more energy here than we put in right here or right here. So you put more energy in, you can go higher or knock out electrons that are in the bottom. Okay, so it's excited states. Okay, so modeling these. Really, there's only two ways that we might model it. Would be in electron configuration, which of course is very closely related to a orbital diagram. Of course, you can interchange those if you want, and maybe a Bohr diagram. That would be the main way we would show that, and I just showed an example of that. So electron configuration, we just have your standard 1s2, 2s. So let's just say we go 1s2, 2s2, 2p, 5. Okay, so now that's, and they might stipulate, okay, you can tell, of course, this is a ground state. And they, and if you were to do something a little more particular, they would say draw write out the ground state electron configuration for fluorine. And they'll say ground state, that means they want the standard way that we've been doing it. You could up that to anything you want. Okay. Technically, it could go up higher. It could be, 1s2, 2s1, 2p6. So we should note that electrons can move. That's pretty important, okay? And there are lots of exceptions to these guys. It's very similar energy levels, okay? But one very common example might be that of the carbon atom. Okay, let's just do that right here. So the carbon atom, okay, so for carbon, we know, all right, exceptions is carbon would be 1s2, 2s2, 2p2. So again, not that this is a huge deal, but you'll find there's a little bit of differences here. That's fine. But let's draw out the orbital diagram for this thing, and it's going to be 2p2, and people find that actually in nature it looks more like this. Arrow up, arrow down, at least the theory at this point. A lot of this stuff is very theoretical, is it looks like that. Okay, and the reason they're saying this is because carbon bonds 4 times, and they think it looks like that. Okay, very difficult to actually verify that, but we're using evidence like solving a crime scene. So there are different variations and there are different exceptions, and we're not super worried about those exceptions right now, or for that matter, it's just the way it is. Electrons can get bumped up to higher levels all the time. Really, it just comes down to be what is the best energy scenario, energy, or the lowest energy profile. So it's kind of like a ball rolling down a hill. Okay, it's not just going to sit there; it's going to roll down all by itself and take its best spot, lowest energy spot. Okay, so where do we see this lots? Okay, our theory here is that we call a flame test, where you take it. We'll do a lab on this, where you take a nichrome wire with a loop on it. That's what we use. You dip it into a chemical, all right, and then you stick it into a Bunsen burner flame. Now, a Bunsen burner flame really is not that much energy, okay? So, and you stick it in here, and you get some different colors coming out. Those colors are reflective of the electrons moving around, shooting up at an energy level and coming back down and giving off a photon of light. That photon is maybe as you from your eyes, okay, you are going to see a color. Now you can't see all energy coming off this thing. There could be all sorts of different types of photons or electromagnetic radiation. That could be so infrared radiation would be, we have color, stuff that we can see would be visible light. So likely we're not going to have anything too much higher than this because that's too high energy. But we could have some infrared light coming off this thing. We could have some radio waves, some very low energy. And if you were a different animal, you could see insects. Sometimes you can see other things, or if you had a detector. But essentially, we're not going to get any more energy out of this thing in the terms of photons than the Bunsen burner put into it. But sometimes we use this as a fingerprint to identify chemicals. Sometimes kids, you're going out here to a campfire, you get yourselves sticks, and you're all sitting around the campfire, and sometimes people will put into this thing a little bit of copper. And people sometimes realize that copper will, turn a nice green color. And you get a nice little green color in your flame. And that is basically a flame test. Okay? And we'll stop there for today. Thank you.